Hello, everybody. I really glad to see you, some of the in person and some online. Today will be one of the lecture related to iBRAIN project and also related to the methods of brain activity analysis called MEG. So my name is Olga Sysoeva and I am actually psychophysiologist, not physicist or any related to mathematics background. And when we talk about MEG, you might think that I will explain you some physics about it, but I will try to focus more on my background and what I know about G from a research perspective. But certainly there will be a little bit of physics too. But stay with me with my background, and that's what will be it about. Okay, and as far as it's a part of the kind of study course, I want to have some interaction with you and some interaction related to your previous backgrounds, your previous lectures you heard. So is it possible that they will answer auditory, or should I see the responses in chat? Because I want to have some questions, answers. Okay. Okay, so what is magnetoencephalography? It's in short MEG. From its name, you can see that it measures magnetic field produced by the brain. But can you guess, like, how much is this field? And here is just relative numbers. So the magnetic field of the Earth is microtesla. So it's 10 in -5. So it's 10,000 smaller than 1 Tesla. And human brain produce even like thousands of hundreds of times smaller field. It's called picotesla. And that's kind of an unimaginable number. So that's why it's kind of very hard and expensive to measure this magnetic field. And what we need for this? And it will be, I'll start with the very simple questions, but that is now hidden on my slide. So what problems, what two main things we need to aware to be able to measure MEG? So any ideas in the group? Guys, we will not continue until you will not answer. What do we need to measure MEG? Like, as I explained it, it's very small amount of magnetic field, picotesla. So what we need for it? The two things. I mean, it's very simple. I mean, as I said, I will start with the very simple questions. Amplifier for what? Yes, the thing is the sensor, the very sensitive sensor, like, you know, certainly with amplifier, but the main thing that sensor have to be sensitive to that very, very small field. Good, that's the first point. Sensitive magnetic field detector. What else? Taking into account that we have magnetic field. Yes. So that's because I think the audience doesn't hear what you said, but the thing is that as far as I have a lot of magnetic field, so we need to kind of prevent from it. And that's certainly magnetic shielded room. So that is also very, very important, because as far as what all of our environment is fluctuates in such a great extent, we need really this, and that is also one of the most expensive things in the MEG. It's this shielded room. I work with MEG in several laboratories in Finland and in Moscow Energy Center, I will tell about it, but even with the magnetic shielded room, we sometimes when the construction was ongoing on the streets around, we have the fluctuation in our detectors. In Finland, in clinics, the lift moving, elevators moving was also seen on the MEG device. So that's even after very many prerequisites, and after building it in a shielded room, the background, this environmental noises are very important. And also on this slide, I wanted to notice the last line. It's about magnetic resonance imaging, and the magnetic resonance imaging. I will talk a little bit also afterwards. That it's induce the magnetic field on the person, and it's there is different machines usually used now 3 Tesla, but that is also not natural magnetic fields for us, because magnetic field of the Earth is like much smaller, 10,000 smaller. That's also related to my net. Sorry, it was, I have to show it previously. That was one of the first magnetic shielded room in left side. It was built in USA in around 1972. And that is currently usually typically magnetic shielded room that have several doors, and well, it has active and passive protection from the environmental magnetic field. And yes, that's about the sensors we talk. So to measure the magnetic field, we need very sensitive sensor, and this sensors which is most typically now used is superconducting quantum inference device, QUID, and indeed it's in a huge part made by hand. Like there was, and I think now still exists in Finland, the huge kind of, not huge, a small manufacturer, then they kind of doing it in a team. Each sensor, a lot of processes requires very much of the personal individual kind of tuning and participation. And the problems of this sensor is that it have to be placed in a very low temperature. And that's why we have the reservoir with helium, which have to be filled every time to froze somehow the device to support the particular temperature we need. And that's just very brief view how it works, physics. And okay, and now let's talk about how MEG is among the other neuroimaging techniques. Here we have the slide, which have a kind of three-dimensional. One dimension is temporal resolution. Other dimension is spatial resolution on X and Y axis. And we also have the dimension invasiveness, which is reflected in the color of the dots representing different techniques. And you can see MEG is less invasive, best in temporal and spatial resolution. And it's almost, not almost, it's actually similar in all these characteristics of invasiveness for IEG, is intracranial EEG recording. You had previous lecture on EEG, and you know that EEG measures brain activity usually from the skull, and that's represented here. It has pretty good temporal resolution, but still it's a little bit worse than in imaging, and I will show you in the slide why it is so. But it has really bad spatial resolution. Here comes my other question. So why it has bad spatial resolution? Now there are a lot of devices which has like even about 256 channels, I think, EEG device. We have like 128 channels EEG device. Why it still have poor spatial resolution? Yes, the distance, why it's the distance is so important, because for imaging we have even further, and there's also the distance. Why for EEG this distance is kind of more crucial? Yes, surrounding tissue, that's important. So for MEG, magnetic fields goes through tissue without any distortion because of the magnetic field. But for EEG current, for electric currents, it distorts. It's distorts in the way it smears down around the skull. And even if you have very many channels, the closed channels amount, they have very smeared signal. And when it's transparent from this sources, we can't get better resolution that we describe here, increasing the number of electrodes, because it's just impossible to because the signal is smeared. If we go through the skull, if we go inside the brain and place it in the cortex, in the case of intracranial EEG, then in this case we have we gain the spatial resolution. Okay, so let's move further. A little bit, couple of slides about other neuroimaging techniques and why they're not the best from my lecture today, because I will today advertise MEG, but the following lecture will be about magnetic resonance imaging techniques by Olga Martinova. I think there you can you will learn that probably fMRI is the best, but stay with me today. And today we will learn how MEG is cool. So the problem is here, that's not, I mean, not a problem, but it's the main principle is that you have magnetic field and you have special also magnetically shielded room where we place this device, and this device measures particular spins, particular processes in the brain, which is quite temporally smeared, so we can't have a good spatial resolution on this. And it's also a little bit invasive, but so we don't place anything inside, but we place a person in a magnetic field, which is they not used to, which is higher than a general environmental magnetic field. And if most people doesn't feel it, but there is cases that you can feel it, especially when now the sensitivity and Tesla points increases. That's 7 Tesla machine. My friends who use it in Germany, they said that some people really feels not very good for when staying for some long time there. And that's my, I think, quite favorite among magnetic resonance techniques is magnetic resonance spectroscopy. I never use it, but I think it's really cool because the principle is similar, that's magnetic resonance imaging, but here you also place the person in a magnetic field, and particular because of the particular spectrum of which emanates from from different particles in the brain, we can quantify the variety of neurochemicals within the particular region and the tissue. For example, how many GABA neurotransmitter, how many something else. GABA is the most studied, and I think it's really cool that we can in real person during real cognitive tasks to measure it, but still it's have poor temporal resolution, and I will show you how important is temporal resolution when we think, and that's why MEG certainly is great. So again, we'll talk about a few words about this SPECT and PET. So that's kind of old-fashioned already, but when I was, I think, your age and university, I was really fascinated and about this technique, and I've been in St. Petersburg laboratory where Bechterew worked, and they showed us like this SPECT and PET positron emission tomography scanners, and that was something really cool for science. But it's much more invasive than fMRI, certainly. It uses specific measures gamma rays emanated from the tissue, but it's first you have to get inside to be injected with gamma emitted radioisotopes, and that's certainly not very pleasant, but you can get really great images of the brain, of the tissues, and everything. It's that's one SPECT is called single photon emission computed tomography, and positron emission tomography is also of the same principle, but it's just different types of phrases that is used to make a picture of the particular organs. Okay, but now it's clear MEG is the best. Okay, so a little bit talk about your previous also EEG measures and what exactly we measure and why our brain produces magnetic field. That's because, yeah, I think I can ask also questions, but I think when the audience answers, nobody hears in the lab. So probably I'll skip this question for the quick movement, because I know everybody understands already of the whole course of the lecture that we have neurons that produce electric currents, and that's why we can measure some electric fields inside our brain. But when these neurons or so-called structures of the brain, if they the signals they randomly represented or randomly oriented or asynchronously activated, we still couldn't get the device the signal enough to measure. So what we can measure from the skull is the synchronously activated parallel oriented neurons, and that's particular neurons, pyramidal neurons in the cortex. That's usually what we measure. And here the concepts of dipoles, so we can kind of consider our brain as a set of batteries, and this pyramidal cells produce the current, electric current, and surrounded by magnetic field, and magnetic fields is usually, you know, the law of magnetic field, that is the current of the right hand thumb. So if the thumb points to how the electric signal goes, the magnetic field goes around it. That's important to answer, because now we'll have in a few slides the questions about it, about the difference, how the brain activity is distributed through the brain and on different types of sensors. Okay, so that is different types of sensors. Also stay with me now, because I will ask a question about this. So we can measure as magnetometer, it measures in Teslas, and it just measures the magnetic field above the activity. The simplest magnetometers that we all know is the compass. When we it measures the magnetic field of the Earth when you go to the forest. Previously we used it sometimes, but I don't know, does contemporary students know what compass means? It shows south and north. I don't know whether we use it somehow, but it's very simple principle, and it just measures magnetic field and shows the direction of the current. It's the similar, but it's much more sensitive, which we use in imaging machine. But it has some problems. So because, and then why a lot of, actually all imaging machine now, as they have not magnetometers, but gradiometers. And gradiometers is actually a combination of two magnetometers, and it can be localized, not localized, but consists of the axial gradiometer, which have two magnetometers in the axial axis, or planar gradiometer, which is oriented planar on the plane. Important here that it's hard to combine them physically, even in you have it in a one MEG machine, because it uses different measures. So magnetometer measures in Tesla, a gradiometer is measured in Tesla per centimeters, because it measures the gradient between these two magnetometers. And so what do you think, why we need these two magnetometers? Why we need gradiometers? What is the advantage of it? Any ideas? Probably there were people with some physical background, physics, or just guess. To not to provide, to for artifacts, to account for artifacts. Yes, because if you have two, you measure the difference. Certainly, it is less sensitive to artifacts and to the general field which is going on around, because it will affect both them. And here you can see that the environmental noise is much more, much less registered in planar gradiometers, because you see as the magnetic field goes, you have the difference, and because it affects both of these magnetometers, it's kind of subtracted, and you have only the signal which is between these planar gradiometers, not goes from outside. Okay, and here also important, it's the sensitivity of the magnetometers. It might seem to you kind of counterintuitive, but in the part of the where the source of the activities, the measurement signal from magnetometer will be 0, and it will change the polarity at this point, and it will be high and positive at one side and negative at the others, just because it measures the magnetic field and it goes around, and it's as the distance change, it's have this curve. And also for axial gradiometers, it's also the same, but it's more kind of tuned to the sources. because there is 2, but still it has 0 here. And the situation is completely different for planar radiometers, because you know, it have 2 signals, and the major difference between these 2 magnetometers will be exactly above the sources. So that's important to understand for our next slide. Not exactly next, but probably in one slide. It's again, it's cortex. Cortex produces sulcus, and the dipoles, which we can, which is because of this particular shape of the sulcus, we can measure. It's usually divided into radial and tangential, and certainly you can think that depending on the orientation of your magnetic sensor, you will be sensitive more to the tangential or to radial sources, just because of the signal. And okay, probably I can ask here a question. So which sources, tangential or radial, will be missed more easily by which sensors? Yeah, which is MEG is used to be believed more sensitive to radial or to tangential sources? It's because of these 2 magnetometers, and they placed above the head, and there is a different gradient in a between 2 sources and the between these magnetometers, and that's more sensitive. If the source is radial, there is no much difference between the magnetic field above it, because the magnetic field goes around the current. Okay, so you're right. Good. So here I describe you one of the MEG machine which used in Finland, and also which is the only MEG machine in Russia, which is in the Moscow MEG Center, and which is now used together with High School of Economics Center for Cognitive Science. It has a great magnetically shielded room. It has smart sensor squids, and usually most of the MEG machine now, they have like around 300 sensors among this, and these sensors in Electra MEG, it consists of one triplet. It consists of 102 triplets, and each triplet consists of 1 magnetometer and 2 planar radiometers. That is exactly because we want to be sensitive to different direction of the sources. Then we need planar radiometers oriented in perpendicular direction, and 1 magnetometer. It's also important addition to the description of the field. But again, remember that we can't combine it easily. We need to do some procedure before combining, because magnetometers measures in Tesla and gradiometers measures in Tesla per centimeters. Okay, that's, oh, I'm sorry, I'm going in the wrong direction. Okay, and also it is important for understanding, because when you work with MEG, and will work with MEG, or if you will read the papers about MEG, which device is used, because the devices have different triplets actually. In electron MEG, you have planar radiometers, and for CTF MEG device, actually now there are only 2 companies that's selling the traditional squid MEG. It's Electra and CTF. And in CTF, you have not planar gradiometers, but axial gradiometers. So the signal is completely different. So you don't, we will see its comparison in a few slides, but physics is different and you can't directly compare them. But what is important, what I'm presenting you one of the recent report that about longitudinal consistency of source space, spectral power, and functional connectivity using different magnetoencephalography systems. So even if you use different magnetoencephalography system based on different sensor, axial gradiometers and planar gradiometers, when you go to the source space after some sophisticated analysis and measure, for example, here baseline versus first follow-up study, and upper line is for alpha rhythm, and this line is for beta rhythm. You can clearly see that regardless of comparison, baseline versus first follow-up versus second follow-up, which is based on different MEG recording system, and baseline versus second follow-up on the different recording systems. This was 7-year studies. So the people, like about 30%, I'm not remember exactly, they come every year for 7 years, some or not every year, but probably even every year, that have at least 5 measurements, but here we present only 3. And they were recorded in different devices. And here you can see that between subject consistency for alpha is really located and occipital cortex, and it's high and it's reliable, and that's what we expect for alpha rhythm. And for beta activity, we have it goes from motor cortex, which is also important, and we also have very great consistency between the different machines. So I think that's pretty amazing. And what they also wrote about in this paper, that within subject consistency was much higher than between subject consistency. So that's that we can get indeed on the individual level, and it's important. So most of our now neuroscience based on the averaging between different subjects, but I think in the future, and the more the techniques develops, we can really get to the single subject data, and such a great numbers and internal consistency. This longitudinal consistency, I think, is inspiring. Here, a little bit about the comparison with MEG and EEG, and why MEG is better. First of all, EEG used relative signal, so we every time have some reference, because we can't measure electric field in one point. We need to have some reference point to measure, and that's actually a huge problem. I mean, it was a huge problem. So now it's a little bit resolved in some new EEG devices, but where to place reference? Because ideally we want to place it in some point where the no brain activity is recorded and no other like electrical activity is recorded. But where it's we can't place it in the air, like, you know. And when you place it somewhere in the brain, we still have some electric currents from muscles, from anything. So you can't never get very pure signal. But MEG measures absolute signal, because we have gradiometers which already within its sensor have a difference, and it's going to indeed show the activity at the particular point it's placed. Other point, we also discussed that it is not affected by difference in conductivity, so the tissue doesn't attenuate, doesn't influence the MEG signal, magnetic field in any way, just the distance. And the distance is kind of important problems, because the signal strength decreases with very quickly with increasing the distance. And it can be advantage or it can be disadvantage. Advantages why it can be advantage that the signal attenuates very quickly. Let's again involve the group. I want somebody from the online stuff. I don't. As they said that there is about 20%. Somebody, please. Why the quick decrease of MEG signal with the distance can be advantage? In which case it's as good?
If we measure cortex activity.
Definitely. So the activity from subcortical region attenuates much quicker, and you can more separate the cortical activities from the other sources. Great. Also, some of the practical good things with MEG is that it's short preparation time, because MEG device, as you say, you don't have to place any electrodes on it. You just sit in the machine, which has MEG sensor inside it. And but still, there are a problem of modeling of the activity, and this modeling is hard for both EEG and image signal, but it's a little bit easy, more straightforward of the modeling of the source, but I will talk about it a little bit later. Here we come to the one important question I wanted to, I remind you about the dipole, about the centers, EEG and MEG, and now goes the question. Here you have the distribution of the signal, of the same signal, but produced by different devices, EEG, MEG magnetometers, and MEG planar radiometers. Which is which, do you think? I will describe a little bit this signal. It's auditory paradigm when the sounds presented to your ears, and you have your brain detects the changes in auditory signals. So they should come somewhere from auditory cortex. But we have three pictures, which will be EEG, which will be magnetometers, and which will be planar radiometers. As you can see, all of them are very different, but it's from the same subject, from the same paradigm. Left, but this one. Let's vote probably for in the group. They can vote for chat, and here we can vote for yes, I think that will be better if everybody writes some of the ideas. EEG, planar radiometers, and magnetometers. We can go back for this a little bit. So how the signal, the current goes, how the field goes, and what and remember also the sensitivity, which gets the sensitivity above the source, which gives 0 above the source. Are there any votes in the chat? Okay. Okay, yes, this girl already answers one time with okay, let's wait just like a couple of seconds and okay, group here, like vote here, and then we have 2 versions there, and okay, in the center, like let's start with the center. What is it EEG? Who is for EEG? This nasty. Is it EEG or not? Oh. The right is here. Okay, who is thinks that it is not EEG and why then? Okay, if it's auditory cortex, where should the signal be in a distribution? Where our auditory cortex here is kind of represented? Yes. Yes. But for planar gradiometers, the major signal will be above the sources. So this is most right picture is actually planar gradiometers. Yes, it's just because it's represent exactly from where is the location. These two pictures, one is EG, other is magnetometers, because all of them they have zeros at the points of where the actual sources goes. But as most of the people might get it right, that it's EG because the signal is more smeared, and here on the magnetometers you clearly have more dipole structures. It's more kind of inverted, and it have two kind of sources. But again, the sources represented now is between the major change in the polarity. So that is middle is EEG, this is magnetic field magnetometers, this is planar gradiometers. And I think if you read the paper something, if you get some of the signal on the topography, it's important to understand that it's not every time the major activity goes from the electrode with the highest signal. In the most cases, it's not like this simple because of the dipole structure. And it's especially so for auditory cortex response, which have our polarity inversion between mastoids and frontal stuff. Okay, I'm glad that some people got it right. And now we are going shortly about the analysis, because certainly the analysis now of the MEG and EEG develops drastically. Previously, I think we can just like first time the Berger measured as a single EEG recording, which was like simply some waves. But now we can average it related to some external events. We can do time frequency analysis. We can then go to the sources inside the brain using the inverted reconstructed from the scalp activity. And you can have different coherence measures. And I will not talk much about, just point you to some potential problems and key concepts in this, because when we talk about image analysis, we certainly talks about source reconstruction, because one of its advantages is combined temporal and spatial resolution. Here we'll talk about spatial resolution, how we can get it. First, we can certainly get in the from the planar gradiometers, which we can indeed kind of show you activity above the points where it is, but we want to go deep inside the brain and to reconstruct it. So that was one of the forward problems, that we have physical sources and we have body tissue and volume conduct and then observed potential. And that is we can easily reconstruct mathematically if we just simulate, we place the sources inside the brain, if we have the measures particular of the volume conductor, body tissue, transparency, you can clearly mathematically define what you will record in the sensor levels. That's not a big problem. It's mathematically probably hard, but you just multiply matrices and that works. But the problem is not that we want to reconstruct the signal on the sensor. We want, on the contrary, we see the observed potential if we want to reconstruct the physiological sources. And in this case, it's called inverse problem. And this problem is actually much more difficult, although it just changed the direction of the arrows here. But the problem here that is mathematically ill-posed and fundamentally ill-posed, because each of the observed potential can be explained by a multiple combination of the sources. And you never know until you have some restriction which is correct. Mathematically, it doesn't have any unique solution. For example, that's simple example. We can, if we think about the brain as a battery, and there is some battery source, and we have three sensors above, and we have particular three measures and these three sensors. Any of this solution can be true. You can have one battery placed closer to the sensor. You can have multiple batteries placed further from the sensor. You can have big one battery placed somewhere in between. So we don't have unique solution. And that's the main thing. But certainly, you know, and you read papers probably, and you know that we do reconstruct the source activity. How we can kind of dare to do this, because it's every time have multiple solutions. So we possess some restriction. Most ways there are several ways to deal with this multiple solution problem. So we can think, okay, we have kind of a few major sources, and we can even predefine some of them position and say, okay, please, mathematical algorithm, find us the best solution with the few sources. And that's sometimes work, especially in this case of the auditory sources and auditory cortex. I can even present you. Yeah, I think I go a little bit further. Yes, to present you an example. This is from my old papers on this mismatch negativity paradigm, when we have sounds which goes to your ears and you hear it, and some of the other sounds can be in different frequency, other can be in different duration. And you just, when you use a single dipole and say, okay, you have 30 or 300 sensors, please computer program, I think that was, I don't know, that was not brainstorm that time, it was some other dipole modeling program, find out the best solution. And we found two sources in auditory cortex which explain like more than 80% of the variance of the signal, and that was placed in a Hirschfeld gyrus. And more even, we can find the difference between the sources which represent the difference in frequency compared to the sources which represent difference in duration, and they can be separated and placed within the brain. So sometimes this restriction that they have, okay, we have few sources, it works, but certainly in the most time it will not work. So other and now most commonly used technique, because now the computer has better power and ability to reconstruct. It's assumed that a distributed dipole model. So it's assumed that activity is everywhere, and you kind of define the pixel in the brain and calculate what can be in this particular pixels. Other technique is spatial filtering, and also now kind of widely used, and I like it. The form is beamformer analysis. It assumes that time courses of different sources are uncorrelated, so it tries to find the most independent sources, and that's in each pixel, and that's keeps only them. But which method to use? It's hard for the researchers, and would be great if the more people will be have some mathematical background and will be aware of all the difference and which method is better to use. And but currently the situation is not that easy and simple. I think I will not go into this constraints. I just show you again some of the examples from the paper. It's from Bailey group. And again, this comparison between MEG and EEG. Here you can see that they have recorded some signal in response to some, I don't exactly know, remember which symbols they used, but they have simultaneous recording of EEG and MEG. And you can see the topography again is different here. You can was it planar or axial gradiometer? Can you say it to me now with the proficiency? This MEG is a planar gradiometer or axial gradiometers. If EEG signal is like this. Excellent. Yes, Christina is helping us. Certainly, because again, it's the sources from EEG, we can get that the sources is somewhere in between. And if it would be planar gradiometers, so the major activity will be here. And here it's just perpendicular to the EEG sources. And we know that when EEG currents go there, the magnetic field goes perpendicular. So clearly they use the CTF machine, not Electra. Okay, and in CTF machine, if they use and reconstruct them to the sources, and they actually simulated the activity here, because they know where the actual source is here, where the actual sources is. And they see that it's pretty nicely convert back to the actual sources. But for EEG stuff, you can see they also have some dots in the actual sources, but most activity, more major stuff, localized in a little bit on the other side of the sulcus. And it's called localation biases. And it's actually a little bit more, not even a little bit more, but with the, if it goes from 256 channel CSG to 64 channel CSG, because they don't have even any activity on an actual sources, and all activity only in the other part of the sulcus. It's less than probably 2 centimeters, but it's already different brain region. That's why I say that because of the smearing of the signal, EEG can not be used for the kind of very precise localization. And here they show it in a simulation. And this bias is also, there is also some other points represented here, but the bias is much less, and we still, for imaging, goes the greatest activity above the real sources. And that's different methods how we can reconstruct, and you can see minimum null estimates. It's good reconstructing occipital and central sources, but it's failed to reconstruct insula correctly because insula sources here, and it's moves the activity more to this part. But dynamic statistical parametric mapping and S-Loretta is pretty good with localizing all the occipital, central, and insula activity. I also advertise one of the methods developed at Moscow MEG Center. It's a group analysis leads to accuracy, Gala technique. And you can read about it more. I will not go to details, but as you can see, new methods emerge, and here the comparison of MEG technique and Gala method. And you can see that there is a different condition placed by red and blue lines, and we can have great differentiation of this condition with Gala technique, and we don't have much with the MEG technique. So the new developing tools well, kind of really extends. So, and we don't know which method is best, as you know, it depends on your assumption, and I a little bit represented it. The dipole is okay when you have clear sources. Beamformer, you have to have an assumption that the sources are independent, and distributed is very much depends on the parameters you use for it. So because and that's you have to keep in mind. So now I will go for them also briefly point with the example on the most important advantages of MEG over AG. First of all, it's great for high frequency oscillation recording, because MEG outperforms EEG here drastically. Some of the researchers in Withman group, I really fascinated with them. They undertakes such a cruel experiment, but they undertakes it on their own bodies. Like they fully they take the curara, which fully blocks all the muscle activities in their body. They were placed in the hospital and they were ventilated for breathing by the external device. So then no muscles of there were working. And then they can see and they perform some cognitive task, and they can perform it with in paralysis and without paralysis, and they can perform it the same as they have quality, but they both of them have greatest when they compare the condition under paralysis or in a real situation, they have greatest difference in the high frequency activities. And sometimes they do it for with EEG, not for MEG, but it clearly represents that in EEG, every time the high frequency activities above 20 Hertz, it's every time contaminated with high frequency, with muscle activity. The extent to which it's contaminated is, you can discuss, you can argue, but it's kind of proved in many papers, but most evident in this group, where they fully block their muscle activity, that you have great contamination of this, and it's completely blocks all the high activities when you just block your muscle activity. And for imaging, it's not the case, because you again, it's the advantage of the imaging that the signals quickly attenuates from the sources. So all the muscles, well, the close muscles, certainly the face muscle can contaminate a little bit, but it's much less. And here you can see even the example from I provide from my colleagues from MEG Center, Kaptelova and Stroganova. They measures MEG for patients with epilepsy, and you can see the very close by channels, which usually in EEG shows very similar activity, and here you can see the really different activity, and we can clearly localize the different brain regions. Other thing which you can't use EEG is measuring the fetal response, because fetus inside the mother thumb, and it's a certainly extreme example, but you can't place the EEG there because it's protected by the womb. And also in some patients, you can't really measure EEG. And in this case, there are new devices that were specifically tuned for measuring the magnetic activity in the womb of the pregnant woman was developed, and that's how it looks like. And they showed that the fetus inside the mother womb, it can separate the sounds of different tones, and it can be like, you know, disentangled within the single subject. And I think it's a great direction to study how the brain of the fetus works. And Yes, that's about the better temporal resolution of EEG, of MEG. It's some people might question it, but I think that is again a clear example from the patient, which was recorded in Moscow Imaging Center. When you do source activation with the close channels, you can really track milliseconds difference in the beginning of the epileptic activity. And it's this localized in different region. And that's important because this is patient who is about to undertake surgery to prevent from the repeated and drug-resistant epilepsy. And certainly for the surgeon, it's important to delete as small part of the brain as possible. But from the other side, they need to delete the sources which is trigger the brain activity generalized. A lot of epileptic activity, it's quite generalized, but it comes from some sources. And to find the sources, you need to have a very clear separation in time. And here you can get it in time and in space. And certainly it's restricts the region, and it's very important. And here a little bit more about the sensitivity of imaging detected epileptic form activity. And again, in most cases, sensitivity of MEG is outperforms and 30% or something. And that's example in which particular region. Yeah, that's that was even. I think that's a great study because it when we do some EEG, MEG, and person, we can't really get to the ground truth. What is ground truth? Okay, we localize, we reconstruct some sources, but what is the ground truth? We never know. We don't have simulation or anything. With the patient who undertakes the surgery, we can get the ground truth, because here is an example when the sources for identified by imaging or EEG, and then when this particular part of the brain was deleted after the surgery, you can see whether the patient is still have the epileptic seizures or it's gone, and how it develops. And here there's a proof that the zone of the resection is every time coincide the main MEG zone, which was detected by imaging, and predict the outcome of the performance. So that's, I think, about the clinical significance. I will skip it. The other point generally, let's say, okay, EEG will outperform MEG because it is not sensitive to the deep sources. I found the paper of k.п.н that was able to detect auditory brainstem response with MEG. So MEG is also sensitive to deep sources. Certainly it's attenuated, but with a high, nice paradigm as auditory brainstem response use, you can indeed localize the sources in the brain stems with different parts. And MEG, that is also example. So how MEG is better than fMRI, because fMRI you can get just the activity with the low temporal resolution, but here the example of MEG study with language, which kind of traced in time, in a particular time phase when the particular region is activated. And that's certainly very important, because when you say about fMRI, it's like seconds resolution, but second is such a drastically big time for our brain. We even detect abstract and concrete words within hundreds of milliseconds. Just imagine what's going on for the 1 second. All the activity of the brain combined, and we can't disentangle it. So that's why where the MEG goes. No, I will not go for this. And I think I also don't have time for this enough, but probably later can tell. I would better go to the new direction of MEG. It might be future of MEG, because as I told you, but we don't discuss it much, that currently as MEG is the best, as you understand, but it's have very bad disadvantage. It's money. It's very expensive. It's very expensive to build this magnetically shielded room. It's very expensive to build this device with the squids and all the sensors, triplets. And moreover, it's very expensive to support this machine, because you have to have this liquid helium replaced every week to support the particular temperature where the sensor goes, and it's the money, and you can't get rid of it. And for science, you know, who works in science, sometimes we have grants, sometimes not, and keeping the MEG machine is very, very difficult. That's why in Russia now we have only one device. And so what can be good? Then we can get warm MEG. So at least we don't have to spend every time for this liquid helium. And I actually was preparing this lecture for 2017, and now a little bit updated. It was first and great. It looks very strange. At the group of Portal, they developed a called warm MEG. It's called optically pumped magnetometers. And here is from that paper of 2017 how the activity is differed between traditionally squid and optically pumped magnetometers. And you can see that optically pumped magnetometers sometimes outperform it, and also is able to detect MEG. And here is more recent paper, and I particularly like that even move it toward that this can be used in the real world application. So just drink a cup of coffee while you in such a, I think, movie star helmet, sitting there is Indian or somebody, I don't know who is that. And they actually, before it's published in Nature Letters, they even perform really moving task. So this girl, it's placed bunch the ball on a rocket. And during this bunching of the rocket, her head even was moving at like with 6 centimeters or something deviation. So it would be not possible for this particular traditional MEG device. And using the beamformer technique, as I said, it's like particular source reconstruction techniques. They indeed localize it in the motor cortex. This beta activity decrease. So when she was bunching, there was no beta activity, but when she rests, it's increased. So this is desynchronization in beta activity, and if they localize the difference, they get it to that particular region. And I think it's kind of promising. But what I wanted to say, that was I prepared for like 2-3 years ago, but now I learned that in Russia there is in Skoltech they develop a similar system. It's already from MEG Center in Russia, so they have this optically pumped magnetometers. They can measure also brain activity, and moreover, they develop even kind of 3rd generation of MEG squids, not squids, sensors. It's yttrium iron garnet magnetometers, and now it's only one sensor is working, and it's presented in a paper by this group. And here are they did at the beginning to show that they indeed measure the brain activity, simple eye closing, eye open task. So that's localize the alpha rhythm, and you can see that indeed opening the eyes decrease the alpha activity, and you can indeed check for the identify the point of the closing the eyes, and both of the senses works fine. And that is about the MEG evolution here. So traditional squid MEG is high temporal resolution, high spatial resolution, but it doesn't have portability and it's cost a lot. For opt MEG, it's also have high both spatial and temporal resolution, but it needs magnetically shielded rooms, but it doesn't need a lot of operational expenses because it doesn't need helium and so forth. And the new devices, it's even can be moved from the magnetically shielded room, but it has to be more tested, but it has such a great signal to noise resolution, and that I think that can even overcome this. That's how they actually advertise this. But the situation now is its points shows where the MEG system is in a world. You can see a lot in US. You can see some in the Europe. You can see even 3 or 4 in the Finland. You can see also plenty in Japan, and we have only one still in Moscow, in Russia, in Moscow MEG Center. So I think it's pretty bad situation. It's better that we move forward, and probably this farm advantage of farm MEG, which is now ongoing in Skoltech, might be promising for us researchers in the future. And so I think it's time to sum up. So I think you learned that the MEG is best. It can measure high frequency oscillation and can measure have millisecond resolution and localize different activity. Also is great spatial resolution. I provided some examples. I think you can now have some ideas how the topography of the different signal looks like. And you're also enthusiastic about one real world MEG, which is coming. Thank you for your attention, and I open to the questions. Here is also some tools, but I don't know, probably for this group it's not important.